Hello, I'm Luis Serrano and this is Serrano Academy, and in this video we're going to learn about the Stone-Weierstrass Theorem. The Stone-Weierstrass Theorem is a very important theorem in mathematics, and it says that every continuous function can be approximated using much simpler functions. This is the type of theorem, like the Universal Approximation Theorem or the Kolmogorov-Arnold Theorem, that could potentially be used in machine learning. Because after all, a big chunk of machine learning is approximating functions using simple blocks. So if you like the potential applications or simply the beauty of mathematics, I invite you to stick around and we'll learn about the Stone-Weierstrass Theorem. So we're actually going to learn two theorems today. First is the Weierstrass Approximation Theorem, which got generalized by Stone to get the Stone-Weierstrass Theorem. The Weierstrass Approximation Theorem was proven by this math genius over here, Carl Weierstrass. Carl Weierstrass says a bunch of functions can be approximated using blocks. I like to see it this way. Let's say the function is this house, and you want to build it with Lego blocks. Well, you have no hope. But you can build an approximation. You can build something similar to it. And the more blocks you use, the closer you will get. That's what an approximation is. So we were happy with this, but then Marshall Stone came in and actually proved a lot more. He said a lot more functions can be approximated using a lot more blocks. How do I like to see this? Well, let's say you want to build a Millennium Falcon, which is way more complicated. You can't really build it using Lego blocks, but you can approximate it. You can build something as close as you want to the actual Millennium Falcon if you use a lot of blocks. So let me get a bit more technical. What Weierstrass says is that continuous functions in a closed interval, don't worry, we'll see what all these words mean. Continuous functions in a closed interval can be approximated using polynomials. So here's a continuous function in a closed interval from one point to another point. And as you can see, it's not very pretty. It has a bunch of spikes, etc. And it can be approximated using a nice polynomial. Polynomials are a really nice class of functions. There's not that many of them, but they can approximate anything you want. So they're like the Lego block. And that's what Weierstrass says. And then Stone came and generalized it. He said, continuous functions, not in a closed interval, but in a compact Hausdorff space, can be approximated using an algebra of functions that separate points. So there's a lot of words here. What's a compact Hausdorff space? What's an algebra? And what does it mean to separate points? So don't worry, we are going to see all of this. So I absolutely love the Stone-Weierstrass theorem, but one of the reasons I love it is because Weierstrass is actually an ancestor of mine. Not an ancestor in the biological way, but in the mathematical way. You see, this one is me, and this is my PhD advisor, Sergey Fomin. His PhD advisor is this guy over here, who is my grandpa. And if you continue that chain, you will get to Weierstrass. So here's actually my great academic grandpa. So I absolutely love Weierstrass and I love his theorem. And I like to see it this way. If functions are these things, then you can get close to them using polynomials. They're like Lego blocks. And if you want to get much closer, then you just use a lot of blocks. And this is the basis of many approximation theorems. So let's get more technical. Here is a function. Now, I don't like this one because, as you can see, it has a jump discontinuity. It has a part where it jumps. Like, you can't really draw it with your pencil. You have to lift your pencil at some point. So those are not good. I want to talk about continuous functions. Continuous functions are those functions that you can draw with your pencil without ever lifting your pencil. You can get to spikes, you can get to corners, you can have straight lines and then a bunch of squiggly stuff, you can have whatever, but you never lift your pencil out of the paper. So a lot of functions are continuous. For example, square root of x, sine of x, cosine, tangent, arctan, logarithm, e to the x, exponentials. A lot of the things you have seen are continuous functions, but there are some that you can't even put as a formula. That's the important part. There's so many of them, they're actually more than formulas. So they can be quite ugly. Polynomials, on the other hand, are very pretty and there's not that many of them. So here, for example, constants are polynomial. The number 4 is a polynomial. Lines are polynomial. So x or 3x plus 4 or any line is a polynomial. Parabolas are polynomial. Anything with x squared plus something x plus some number are polynomials. Anything basically where you have a sum of x to the some power times some number, and you have a finite sum of them. They can't really go on forever. Those are polynomials. So they look like this. an times x to the n, that's the biggest term, and it's finite, plus an minus 1 x to the minus 1, all the way to plus a0. You're not going to have x to the minus 1 or to the negative exponents. You have x to the 0 all the way to n. So polynomials will look kind of like this. They're nice, continuous, and very smooth. and differentiable. So continuous functions don't have to be differentiable, but polynomials are always differentiable. They're really nice functions. And you can think of them as anything I can build using finite blocks. 1x, x squared, x cubed, all the way to x to whatever I want, but only a finite number of these. If I take a linear combination of a finite number of these, I get a polynomial. Now, these are the Lego blocks, and those are the things we want to approximate. And Weierstrass Approximation Theorem says that polynomials approximate functions as closely as you want, as long as you're inside an interval. When you go on forever to infinity or plus infinity, that doesn't work. But if you're in a finite interval, then you can get as close as you want using a polynomial to any function you want. You give me a function, I will find you a polynomial that is as close as you want. That's the Weierstrass Approximation Theorem. So this is actually not intuitive if you look at it like this. Continuous functions are a humongous set. There's so many of them. Now let's restrict to continuous functions in an interval AB. Anytime I say continuous functions today, I'm going to say in an interval AB. Sometimes I will not mention it, but I mean inside an interval AB. There's lots of these functions. And polynomials, there's not that many. They're a small set, a very, very small set. However, the picture does not look like this. Weierstrass came in and said, no way. There are a lot less polynomials, but they're not over here in a little set by themselves. No, no, no. They're all over the place. As a matter of fact, they're all over the place. They pretty much cover the whole thing. But why? If there's so few of them, how can they cover the whole thing? Well, what we mean to say is that they are dense. So wherever you look, you will find polynomials. You'll just find a lot more continuous functions that are not polynomials. So for example, if I tried to get a little set like this that contains no polynomials, I will fail. There will always be polynomials. And the more I zoom in, the more I will find polynomials. However, there's still not that many. And that's strange, right? That's a little strange. The first time I saw it, on the second and the third, looked really strange to me. But what Weierstrass actually meant is that polynomials can get as close as you want to any continuous function. So for example, pick a continuous function, this one over here, it's just there. Now, if I pick a random one, pretty sure it's not going to be a polynomial. It'll be like finding a needle in a haystack. However, I can get really close to this function using polynomials. So I can get, for example, a polynomial here. Oh, you want closer? I'll get one here. You want even closer? I'll get here, here, here. I can get as close as I want. Another way to see it is this. Let's say you have your function and pick your favorite number. Pick your favorite radius and make a circle of that radius. I guarantee if the radius is not 0, even if it's tiny, you will find a polynomial inside that circle. And if you want to make that radius a lot smaller, you'll find another polynomial here. It's kind of like the rationals and the reals, right? Like let's say I have the real numbers and let's just think of them from 0 to 1. Doesn't really matter. In this line, I assure you most numbers are real. Let's take some real numbers. For example, 1 over pi. There's logarithm of 2, there's 1 over e, there's 1 over square root of 20, sine of 1, and a bunch of them that I can't really express. As a matter of fact, this is something counterintuitive. When you imagine a real number that's not rational, you imagine something weird, right? Like arctan of square root of pi to the logarithm of cosine of whatever you want. But see, this is not a weird number. That number is very special. It can be expressed using all these beautiful functions. That's a really special number. If you take a random real number from the vine, I assure you it's not very likely that it's going to be written in a nice formula like this. It may not be something we can express as a formula. It may just be a string of digits that goes on forever and never repeats and there's never any pattern involved. That's the majority of real numbers. And then among these real numbers, there are the rationals, which are very special real numbers. They're the ones that you can express as an integer divided by another integer. So for example, 1/2, that's pretty. 2/3, very pretty. 1 over 10, 89 divided by 99, anything. Anytime you get a number divided by another, two integers, we get a rational number. So as you can imagine, they're very special. And there are very few of them. However, even if they're few, they're all over the place because the rationals are dense on the reals. So wherever you take a little interval, guarantee you'll find a rational there. You'll find a lot more reals, but you'll find a lot of rationals. You can't find a little interval that contains reals and no rationals. They're all over the place. For example, if I pick a real number and I pick any non-zero radius, guaranteed you'll find a rational there. So there's still a lot more reals than rationals, but rationals are dense on the reals. So I can actually approximate any real using rationals, and that's actually pretty easy. Think of the number pi, for example. 3.14159 goes on forever. Well, I can approximate it using a rational. For example, 3 is a rational. It's 3 over 1. That's an approximation. Oh, you want to get closer? 3.1, which is 31 over 10. If you want to get even closer, 3.14, which is 314 divided by 100. And you can get as close as you want. 3.141, for example, is 3,141 divided by 1,000. And you can get as close as you want by simply taking as many decimals as you want and divide it by 1 and that number of zeros, and then you get as close as you want as an approximation of pi using rationals. So that's what happens with reals and rationals. There's a lot less rationals, but they're dense on the reals. You can approximate any real with rationals. Well, Weierstrass says the same thing happens with polynomials and functions. The polynomials are a very nice and small set, but they're dense on the space of continuous functions, even though there's still a lot more continuous functions than polynomials. So if we have our polynomials over here and our continuous functions over there, then you can get as close as you want if you use a lot of blocks. And what do I mean by blocks? These blocks over here. So you're going to be needing very high degree polynomials to get close to really weird random continuous functions, but you can do it. And what do I mean by building blocks? This one's over here. So I may need a lot of these to get close to a function, which means that if I have a really weird function, I can get close using a polynomial, but I may need one of really high degree, but that's okay. So these are going to be the building blocks of continuous functions, basically. You can get as close as you want using these building blocks. So let's look at a small example. Let's say that ugly function over there with spikes and squiggly lines and straight lines, that's definitely not a polynomial, but I'm going to approximate it using some building blocks. So let's take the building block 1, and let's take x. With 1 and x, I can make any line in the plane. So for example, the line minus x plus 3 looks like this. And that is some kind of sloppy approximation of the function, but I can do better. Let's throw in one more, x squared. So I'm going to come up with this one, minus x squared minus 3x plus 4. That one is still bad, but it's a little closer. You can see how the more blocks I add, the closer I get, right? Let's throw in some more. So let's go from 3, I get x cubed plus 4x squared plus x minus 6. Well, that one's just a little better. At least it's capturing the form. So you can see the more building blocks I get, the better. Now let's add more building blocks. So let's add all the way to x to the 8. That means I'm going to have all polynomials of degree 8 that look somehow like that. And their drawing is something that goes up and down at the most 7 times. Now, if you're keeping track, this graph is not meant to fit that formula over there. I made some random numbers there, I gotta confess. But as you can see, this is a much better approximation. It almost starts looking like that function over there. It's not exactly the same, but we're getting closer and closer. So now it's a good time to define what do I mean by approximation? Because we have some vague idea that says if they look similar, then it's an approximation, but we need a formal definition. So here's a formal definition. Pick a small distance, okay? Maybe this or this or this, whatever you mean by small. So let's pick that one over there. And now say your approximation needs to be within yay distance of the original. So if I put them over here, then it has to be within that interval where I basically take the function and I move an interval around with it. It needs to live within those walls. Now, if I make the distance much smaller, then I have a much narrower space over there, so I need a much better polynomial. Maybe I need to go all the way to degree 80, and I get some polynomial like that, and that now fits within those more narrow walls. And the idea is that no matter how small I make that distance, as long as I make it bigger than 0, you can pick the smallest number you can imagine. Well, for that number, there's going to be a polynomial, maybe of degree trillions and quadrillions, doesn't matter, but there's going to be some polynomial that fits within that little distance of the original function. That's what it means to approximate. And remember, this only needs to happen in a small interval from some number A to some number B. It can't go outside of that. The interval can be huge, but it needs to be an interval. So what does that mean? Well, within this interval AB, the functions are really close to each other. However, outside of the interval, anything can happen. These things could go super far away. That doesn't matter. The important thing is that within the interval, the approximation is really close. So that is Weierstrass Approximation Theorem. Within some interval AB, which can be big, can be small, doesn't matter. If you pick some continuous function, I will be able to find a polynomial, no matter how big the degree, that gets as close as you want to your original function. So whatever close you pick, I pick a polynomial. If you pick much closer, I'll pick a bigger degree polynomial, but it can always be done. That is the Weierstrass Approximation Theorem. So now we can get to the Stone-Weierstrass Theorem. Now, if you like this video so far, go ahead and hit that subscribe button. That'll help me make more videos for you, and that will also help you get notified of videos like this one. So the story goes like this. In 1885, Weierstrass proved his theorem that every continuous function in a closed interval can be approximated by polynomials. He looked at it and saw that it was good, so he was happy about it. Well, many years later, Stone came in 1937 and he said, "Hold meine Bier." Well, actually, he wasn't German, so he must have said, "Hold my beer," but I needed to be German for my joke. And he said, well, there's a lot of things in that theorem that we can generalize. For example, I don't need the continuous function to be in an interval. It can be in a compact Hausdorff space. So right off the bat, this means you can go in way more dimensions. See, those are in 2 dimensions, but he went nuts. He went in way more dimensions. So the functions no longer have one input, one output. They can have a lot of variables. And then he said, well, I actually don't need polynomials. We can do with even less special functions. All I need the functions is to separate points. So don't worry, we're going to learn what all these things mean. But basically, he proved the Stone-Weierstrass theorem that says that any continuous function in a compact Hausdorff space can be approximated using an algebra of functions that separate points. And as I said, all the words here that you don't know, we're going to define them very soon. So let's start by defining what is a compact Hausdorff space. So there's a lot of big words in this sentence. In particular, let's look at the first one. What does it mean to be compact? The formal definition is that every open cover has a finite subcover. However, this is for very strange spaces that you actually need that definition. Let's work in R to the n. We'll see what R to the n is soon, but imagine just either 2-dimensional space or 3-dimensional space or 1,000-dimensional space. That's R to the n. If you like machine learning and data science, this is the space where most data sets live. So if you are in one of those nice spaces, then all you needed is to be closed and bounded. So let's forget that compact means that definition over there for now. And let's think of compact as closed and bounded. And I will tell you what closed mean, and I will tell you what bounded means. But first, I'll tell you what R to the n means. So R to the n is what most of the spaces that we can imagine in real life are. R to the 1 is simply a line. So a line in particular has one coordinate. Everything in a line is one number. So think of the number line that extends to infinity in both directions. What is R2? Well, R2 is the plane. So in the plane, points have 2 coordinates, x and y. Think of it as the plane of pairs of real numbers. What's R to the 3? Well, that's 3-dimensional space. So a cube that goes on forever, and in a cube, points have 3 coordinates. The length, the width, and the height. So that's R1, R2, and R3, the ones that we see with our eyes, but we can imagine Rn, right? Rn is just a cube of n dimensions. I can't really draw it, but in Rn, every point has n coordinates. Now I switch from x, y, z to x1, x2, x3, all the way to xn. But if you imagine, for any n, say 1,000, all the 1,000 tuplets of numbers, they form R to the n. We call that n-dimensional space. And all or most of AI happens in here because most data sets fit in Rn. Most data sets consist of points that have n coordinates for some n, no matter how big. So that's why I like to think about Rn. But if you're a mathematician or if you really care about the theory behind this, you can think of compact Hausdorff spaces. But in Rn, this means closed and bounded, as I said. What does closed and bounded means? Well, luckily in R1, it means you have an interval from A to B that contains the points A and B. That's very important. An example of closed and bounded in R2 is a square, for example, or anything that's contained, and that contains its boundaries. So in R3, for example, cubes are closed and bounded, and in Rn, some kind of hypercube is closed and bounded. So I haven't told you what closed means, but bounded is easy to see, right? Bounded just means that you don't extend forever. Right? You are held in some big cube. If you fit on a cube, no matter how big, you are bounded. So it means you have limits. You don't extend forever in any direction. And what does closed mean? That is a beautiful definition. So there's actually 2 definitions. One is an open set, and the other one is a closed set. And in short, a closed set is one that contains its boundaries. See, all the points here belong to the set. An open set actually doesn't contain its boundary. It contains everything inside, but when you get to the boundary, it's not in the set. How do we formalize this? Well, Take a point in an open set. This is a point in the interior. Well, if you are in an open set, any point around it, I can take a little ball around it and it belongs to the interior. That's what it means to be the interior. So closed sets also have an interior, because if I take a point in the interior, all the points around in a little neighborhood are also inside the set. However, there are special points in a closed set which belong to the boundary. And if you're in the boundary, then you're pretty much bordering the outside of the set, meaning that if I take a little set around this point, there's always going to be points outside of the set. So to summarize, an open set does not contain its boundary, and a closed set contains its boundary. There's actually a beautiful analogy that one of my favorite math educators ever, his name is Frank Sorcito. Actually, he's one of my heroes. I try to emulate his teaching style because it's the most amazing teaching style I've seen. And he has the following analogy. He says, when I imagine an open set, I imagine something like a cloud. Why a cloud? Because if I take a point inside a cloud, well, I can always take a little bit of cloud around it. It's not going to be in the boundary, right? If I take a point inside a cloud, anything around is still cloud. On the other hand, a closed set is like a pizza. See? If I take a point in the interior of a pizza, then everything around that point is pizza. In other words, I can put a pepperoni on top of that point, and the whole pepperoni is going to be inside the pizza. And if the point is really close to the edge, I can take a much, much smaller pepperoni. And if you pick any point in the interior, I can take a pepperoni so small that is going to be containing the entire pizza. However, if you happen to pick a point in the boundary of the pizza, in the edge of the pizza, then there's no pepperoni small enough that I can put it and that it won't spill out. No matter how small a pepperoni I put, a little bit of pepperoni is going to spill out of the pizza. So a closed set is like a pizza, and an open set is like a cloud. Thank you, Frank. So now we have our definition. A closed and bounded set is one that, first of all, contains its boundary. It's not going to have these parts where it spills over, where there's no boundary, but the whole set is there. And also, it is contained in a big cube. No matter how big, it's going to be contained in that big cube. So that's what it means to be closed and bounded. And for practical purposes, as I said, if we're working in R to the n, that's what it means to be a compact space. Now let me tell you what Hausdorff means. Hausdorff is actually a slightly weird definition because in Rn it's obvious. For a space to be Hausdorff, it means you can actually separate the points. What does that mean? Well, if you have 2 points and the points are not the same, no matter how close they are, then I can separate them, meaning I can take a very small, no matter how small, open set around one point and a small open set around the other point and have those open sets be disjoint. So they have no points in common. So in a Hausdorff space, I imagine that points can't really fight each other because there's 2 points that are fighting each other. I can take a little fence around this one and a little fence around this one and completely separate them because their regions are disjoint. So this seems obvious, right? Because in Rn, I can take any 2 points and a really tiny ball around them. But you'll be surprised, some spaces are so weird and the open sets are defined in such a weird way that you're unable to do this. But as I said, Rn is a Hausdorff space, so we don't need to worry about the definition if we're working in Rn. So now we have everything we need. In particular, any cube in R to the n is closed and bounded. And for data scientists or anybody interested in machine learning, this is beautiful because all data sets, at least all the ones I've seen, belong inside a cube in Rn, no matter how big they are. For example, MNIST. Well, MNIST is a bunch of 28 by 28 images. That means it's a list of 784 numbers. 784 is 28 times 28. So all images in Rn belong to a cube in R to the 784. Now let's look at CFAR. CFAR are images of 32 by 32 by 3 because there's 3 colors, R, G, B. And so CFAR lives inside a cube in R to the 3072, which is the product 32 times 32 times 3. Now the set of language, ChatGPT or DeepSeek or anything like that, well, that lives inside R to the 1024 because that's the length of most text embeddings. Actually, some are bigger, some are smaller, but all of them are around R to the few hundred to a couple of thousands. What does that mean? Well, every word gets sent to a vector of roughly 1,000 entries. So no matter how big language is, it fits inside a cube in the space R to the 1024 or somewhere around that. So we're close to done, right? Let's recap. Weierstrass said polynomials approximate continuous functions in an interval AB. And Stone said, well, I don't need an interval, I need a compact Hausdorff space. We know what that is. And he also said, I don't need polynomials, I need functions that separate points. So now let's look at what this means. What is a function that separates points? And you're gonna love this because it's super simple. Check this out. Here is a function and I want to approximate that function. So I'm going to give you some blocks and I'm going to say, well, I'm going to use these 4 blocks over here. And I'll tell you, hey, I think you can approximate that function using these 4 building blocks. You can add them, you can multiply them, do whatever you want. But you're a bit suspicious. Could you tell me why I am actually lying? It's impossible. And feel free to pause the video and think about it. It's tricky, but there's a really interesting reason why those 4 blocks have no hope of approximating that function over there. If you want a hint, here's a hint. Let's look at the position of 1 and 4. And let's look at 1 over here and 4 over here. So now, feel free to pause the video and tell me why, looking at 1 and 4, there's no way these 4 building blocks will approximate that function over there. And the reason is, check this out. For each one of these building blocks, f of 1 and f of 4 are the exact same value. So f of 1 is f of 4 in the first function, in the second function, in the third function, and in the fourth function. Now, check out 1 and 4 in that one over there. F of 1 is different than f of 4. And so there's no way these building blocks could build me anything close to that function over there. Because whatever I do with these blocks, if I add them, if I multiply them or multiply by a scalar, anything I do, f of 1 is always going to be the same as f of 4. They're attached. And I need them to be different values. So there's no way. I need at least one block, at the very least, one block where f of 1 and f of 4 are at the very least a tiny bit different, because otherwise I have no hope. So I probably need a lot more, right? Well, what Stone said is, nope, that's all you need. So all I need to be able to approximate any function is that for any pair of points, there's at least one function for which f of those 2 points is different. Even if it's different by a tiny amount, doesn't matter. As long as there's at least one function that makes them different for any pair of points, then I have a set that approximates any function. I may need a different function for each pair of points, or I may need one function that separates all the points. Doesn't matter. As long as for any pair of points, I can find at the very least one function that separates their values. That's it. I have a universal approximating set. And to me, this is mind-blowing because it's such a simple condition. I mean, Weierstrass said polynomials. Polynomials are really special. This guy came and said, I need them to satisfy this one tiny thing. And that's it. That's crazy. Blows my mind. So to summarize, what Stone says is, I don't care what the building blocks are, as long as for any x and y, at least one of them, call it f, satisfies f of x different than f of y. And so we are done, right? Wait, what? Oh, I'm sorry, Mr. Stone. We are not done yet because he said something more. He said an algebra of functions that separate points. What does an algebra mean? We're used to thinking of algebra as a branch of mathematics, but he meant something different. There's actually a thing in math that's different. That's called an algebra. So what is an algebra of functions or an algebra of things? And it's just a particular set with some conditions. So for example, a vector space is a set with some conditions. Well, an algebra is a set with some conditions. So let's see what an algebra is. So let's think of some building block functions. Some nice ones are y equals 1. Here's a constant function that's always 1. That's a beautiful function. Let's think of another building block. Y equals x, the diagonal. One of the simplest functions that there is. Now, how can I combine these 2 building blocks? Well, for example, I can add them. I can take x plus 1 and I get y equals x plus 1, which is a line that's just a little bit above. Now, what else can I do? I can multiply by a number. I can multiply by a scalar. So for example, if I have y equals x, then I also have y equals 2x or 3x. Or minus 5.7x or pi x. Any number, I can multiply it by the function and I can use that as a building block. So now I can take 2 building blocks and add them again. So I can take, for example, 2x and 1 and get y equals 2x plus 1. So as you can see, I can start getting any line of 1 because a line has the equation y equals mx plus b. Now here's one more thing. If I just do this, I get a vector space, but I can do one more thing. I can combine them by multiplying any two functions that already exist there. So for example, I can take y equals x and y equals x again, and I get y equals x squared. So that's pretty special, right? Now I have x squared. Well, I can also take x squared and multiply it by x, and I get y equals x cubed. So in particular, I can get x to the whatever I want, right? All I have to do is multiply y equals x as many times as I want. And now I can multiply these by scalars. So for example, 2x and x cubed, now I get y equals 2x to the fourth. And since I can add them too, I can add as many of them as I want and get pretty much any polynomial. So I can get 2x to the 4 plus x cubed minus x minus 1. Any polynomial you want, you can obtain by taking the building blocks 1 and x and allowing yourself to add them, to multiply by scalars, and to multiply them by each other. That's what's called an algebra. So in an algebra, you can add things, you can multiply by scalars, and you can multiply things inside, and you will always stay within the algebra. So it's a pretty big thing. Now, what if I took this condition away, the condition of multiplying things? Then I'm only allowed to add and multiply by scalars. I'm no longer called an algebra, now I'm called a vector space. So vector spaces are very important in linear algebra, but the moment you start multiplying things, you get into higher grounds. So an algebra generated by 1 and x is much bigger than the vector space generated by 1 and x, because the vector space is just lines and the algebra is all polynomials. And so as you can see, now the Stone-Weierstrass theorem and the Weierstrass theorem start getting similar, because Weierstrass said all polynomials and Stone-Weierstrass said an algebra of things, which you can multiply like polynomials. But Stone went much farther than polynomials, because if you start with 1 and x, you get all polynomials. But if I start with, for example, these three functions, as long as they separate points, then the algebra they generate, which means you combine them in every possible way, you can add two of them, you can multiply a bunch of them, you can multiply by scalars and add them, you can get a bunch of functions. Well, rest assured that if they separate points, then you can use these building blocks to approximate any continuous function you want. And so as I said, the Stone-Weierstrass theorem implies the Weierstrass theorem, because if I just take as my original building blocks 1 and x, notice that those separate points, because the function y equals x separate points. If I have 2 points that are different, for example, x1 and x2, the line y equals x sends them to different points. So separating points is actually quite easy. All you need is one function that separates all the points. And with those two, I can build x squared, I can build x cubed, I can build x to the fourth, I can build anything I want, and then I can build any polynomial that I want. And that means that Stone-Weierstrass theorem implies the Weierstrass theorem. The Weierstrass approximation theorem is a particular case of the way more general Stone-Weierstrass theorem. Now here's something interesting. The Stone-Weierstrass theorem says, with such and such building blocks, I can approximate any function for you. For anybody interested in machine learning, this should ring a huge bell, because every time machine learning sees a theorem that says I can approximate any function with such and such blocks, a new machine learning model is born. Why? Because machine learning is all about fitting data sets, fitting functions in data sets. And if a data set is modeled by some weird function, then if you find a nice set of building blocks that will approximate that, then you have a nice machine learning model, which is what happens with neural networks. See, the universal approximation theorem is the basis for the existence of neural networks. If you want to learn more about that one, check out this video on my channel, the universal approximation theorem, why neural networks work. But in short, the universal approximation theorem says if I have a bunch of building blocks, which in this case are two-layer neural networks, by that I mean neural networks that have only one hidden layer in the middle, then those can approximate any function. Of course, inside a closed bounded set in Rn, which is where all data sets live. Well, the Stone-Weierstrass theorem says our building blocks are now functions that separate points. But the reason this is not used in machine learning yet is very subtle but very important. See, for this, I can combine them by adding them, by multiplying by scalars, and by multiplying them by each other. The universal approximation theorem says the building blocks that build these neural networks can be combined by adding. And by the way, when I say adding, I mean finite sums. I can't add infinitely many of them. That's implied. I can also multiply by scalars, and that's it. The universal approximation theorem says nothing about multiplying them. You cannot multiply these building blocks that build neural networks. And it turns out that that's the reason why you can use that in machine learning, and this one not yet. See, here we have an algebra of functions, and there we have a vector space of functions. And this is a lot more complicated, because when you start multiplying things, then things get difficult computationally. This is what I mean. If I'm allowed to add things, and I'm allowed to multiply things by scalar, those operations are fast. On the other hand, if I am multiplying functions, that operation is slow. It's not just that. If I take derivatives and I multiply something by a scalar, then the derivative is the scalar times that. So for example, if I know the derivative of a function and I multiply that function by 5, then I have to multiply the derivative by 5. That's easy. If I know the derivative of two functions, then I know the derivative of their sum because I just add the derivatives. But the derivative of a product, it starts getting complicated. If I have a product of many functions, that derivative gets ugly. So that's the reason why we haven't used the Stone-Weierstrass theorem yet for machine learning, because computationally, multiplying is hard. I really just want to add things and multiply by numbers. I don't want to multiply things by each other. So who knows? Maybe we can get better computationally, or maybe we can find tricks to make this work out. Maybe that can be you. Why don't you help me think of this problem? How can we use the Stone-Weierstrass theorem to come up with a machine learning model that will approximate any function, and thus that will be able to fit any data set in a nice way? I'll leave you with that question. Feel free to put any thoughts in the comments. And with that, I want to thank you for your attention. If you want to continue seeing this type of videos, please subscribe to my channel and you'll get notified. And if you want to be even more involved and help me more, feel free to join the channel or support me on Patreon. If you join or support me, you can get some interesting perks like early access to videos or Q&As with me, or even your name on the videos. Of course, my videos will always be free, but if you support me, you'll get some fun perks. You can also follow me on Twitter, or check out my page Serrano Academy, or check out my book, Rocking Machine Learning. Here is a discount code, Serrano YT. The link and the discount code are in the comments of the video. So thank you very much for your attention, and see you in the next video.